Okay. The last problem we just did using the shell method. We're going to do the same problem using the disk method if we can get our pencil right. Alright, I'm going to write big. It's y equals square root of x. Y equals x squared. Okay, looks like that. And it's going from, if it's x 0 to 1, that's here, here, the area is here. We're rotating it around the line. What is it? Y equals x minus 2. X equals the line x minus 2. No, the line x equals minus 2. That line. Now you're going to rotate it. We just did the we're using the shell method. We found the area to be something. Alright, we're going to do this. The wash, we should get the same. We're using the disk method now. We should get the same answer. Alright. Disk method, we take the revolution, the axis of revolution, and we look at a line perpendicular to that one for our different radii. Okay, so this is going to be our line. We have an inner radius and an outer radius here. Okay, so we're going to have our outer, it's going to be pi r squared. That's just a regular area. We're going to integrate that, so it's going to be that times some other thing. The outer radius squared minus the inner radius squared is where we're going to go with this. The reason why, intuitively, we need to see if this thing is rotated around, we're going to have kind of like a three-dimensional donut or something like that. And we're going to have an inner radius. Can you see that? We're going to have an outer radius. Basically, we're taking the whole cylinder with the outer radius and everything, and we're taking the inner cylinder away from it. So it's going to be the outer minus the inner. Okay, so the outer in this instance, how do we determine this? We know in this instance is going to be a dy integration. Okay, because we're going. I wonder if you can see that. Can you see that? We're going from 0 to 1. We know that. Is even seeing this square root of x. This is tremendously sloppy. I'll write it over. Alright. We're going to take the integral. It's going to be a dy integration. We're going to go from 0 to 1. We know that because we're perpendicular. We're using, when you do the washer method, you go perpendicular. You have little small washers, and then you integrate up. Okay, so up the y-axis. So it's going to be a dy integral. All right. The washers are going to have an inner radius and an outer radius. The formula for area of a circle, pi r squared. Okay, so you have an inner circle and outer circle. So it's going to be pi r squared for the inner, or for the outer, minus pi r squared for the inner. I need to write bigger. Alright. How do you know what the inner and the outer is? Okay, so the outer, we're going from here to here, to the outside. Alright, so it's this curve. Alright, so now what is this curve? This curve is y outer. It's y equals, which one is this one? This one is x squared. Okay, but now we said, do we have a dy integration? Okay, so we wanted the integral in terms of y. So we want y is in our integral. Excuse me. We want y is in our integral. So we know if y is equal to x squared, x equal to square root of y. Okay. So the inner, that's this one up here. Go from here, our axis, to here. It's going to be inside. And the way to think about this is you're rotating it around. Okay. So this is going to be inside. Just try to picture this leaf. Rotate it around. You'll have this. You have a cylinder inside of a cylinder. You're going to take the outside and take the inside, subtract the inside from the outside, and what you're left with is that donut. Alright, think of it as a donut. It might not look like a donut, but it's an outer minus an inner. So the inner is this curve. Okay, this is y equals square root of x. If we want it in terms of y, we know x equals y squared. Okay, so the inner So we know this is 2, and we're going from here to the outer. So this is going to be 2 plus x. Okay? I wonder if that's going to be intuitive. This is we're going from, this is our axis of revolution here. So we have this distance here. It's going to be 2 plus whatever we have here. Okay? So what is this? This is x. So we have, for our outer, it's going to be 2 plus that x, which is equal to square root of y. This one is going to be 2 plus this x, 2 plus y squared. Okay? I wonder if that's going to be clear. It's probably not. I might have to explain it again, but I'll make another video. So, pi r squared outer minus pi r squared inner. Alright? We have pi. The radius outer is this. So 2 plus, I'm going to say y to the 1/2 squared. Okay, this is our outer. Alright, this is equal to 2 plus y to the 1/2, 2 plus y to the 1/2 is equal to 4 plus 2y 1/2 plus 2y 1/2. Y to the 1/2 times y to the 1/2 is equal to plus y. Okay, so this is equal to 4 plus 4y 1/2 plus y. Alright, that's our outer. Alright, now inner squared, pi inner squared. Okay, inner squared is equal to 2 plus y squared squared is equal to 4. 2 times 2, 2 times that is plus 2y squared. Alright, y squared times that is plus 2y squared. Y squared is plus y to the 4th. Okay, so that's that one. So we have that. So we have this minus that. So it's that minus 4 minus 2y squared minus 2y squared minus 4. I should have made that 4y squared here. I'm gonna cross this one out. It's janky. Alright. We have 4 and 4 here, so we cross that out. So what we're left with is, we're gonna go in order of we have 2 y's, so this is going to be y to the 4th from here. Okay, so I'm gonna start right. This is the same as this. 4y 1/2 plus y minus y minus 4y squared minus y to the 4th. All this is going to be times pi. We have a pi outside, remember, and this is a dy integration. Okay, so we're going to take the integral. We're going from 0 to 1. We know that because our figure goes from 0 to 1. We know where it meets up top. So this is going to be, we're going to integrate here. So this is 4 times, this is y to the 1/2, so this is going to be, add 1 is 3/2, so it's 2/3 y to the 3/2, okay, plus 1/2 y squared minus 4 times 1/3 y to the 3rd minus 1/5 y to the 5th. Okay, we got a pi out here. Now we've integrated, we take the dy away, and we're going from 1 to 0. So the math should be easy because we're just going to do the 1 and the other ones are going to fall out. So we'll have 4 times 2/3 is 8 over 3 plus 1 over 2 minus 4 over 3 minus 1 over 5. The algebra is taking longer than the calculus, but matter of fact, the arithmetic. So this common denominator is 60. So 8/3 is this 20 goes into 20 times 8 is 160 plus 1/2 is equal to 30 over 60 minus 20 times 4 is 80 over 60 minus 1 over 5 is equal to 12 over 60. So this times pi, so this is 160 plus 30 is 190 minus 80 is 110 minus 12 is 98 over 60 times pi. That reduces to 49 over 30 pi. And the answer is 49 over 30 pi. Alright, but to recap though, first the washer method. I made a bunch of scratch notes on my paper, but the washer method, we have this leaf, we rotate it around the line y equals -2. We made a bunch of washers. This is a rectangle. Alright, and then we rotate that. That makes a cylinder. It's like we said, it was a can of soup. Okay, and we take that and we that's one shell, and then we're going to take a bunch of shells. We're going to integrate, but one shell, we draw it here. We crack the can of soup open. This is the UP. This is the SO, just so you can kind of see it graphically. This is the we have length times width times height. This is equal to the circumference. It's 2 pi r. We know that r in this instance is 2 plus x, so it's 2 pi times 2 plus x. The radius is equal to 2 plus this thing. Long story short, we end up with 49 over 30 pi. Alright, that was using the shell method. Okay, totally different method on this side. The washer method. Same leaf, but we have in this instance a dy integration, because we're going with discs and washers. Okay, so we have a little disc here, a little disc here. So in this one we have whereas before we had that can of soup, now we have like a donut, and we're taking the outside minus the inside. You probably can't see it, but we did the work. We end up with 49 pi over 30. This is a really rough beginning. We'll try to do better.